Okay, here we go. We're live. Hello everybody. I hope everyone is having a great time studying for midterms. I am doing all right, I guess, but I'm not sure for everybody. Welcome to the CPS 688 midterm study session. So, this study session is going to give you all a nice little recap on everything we learned so far, so that you all can also prepare for the midterms yourselves too. So, let's take a look at what we have here. We're going to work. We're going to take a look at stable matching, which is what we have uh, as part of an introduction to the course. We will also recap on graphs, and then we will get into some greedy algorithms, which are mostly recaps. Um, we will also take a look at some newer ones like backtracking, dynamic programming, and also we will look at the divide and conquer and some NP complete problems. Wow, that's neat. So for your reference, here are some of the credits I would like to give. Firstly, thank you again, Jasper Cruz, for making the notes. Secondly, I would really like to thank Adam, who also provided some notes for us. And finally, I will also send you a nice link to my tutorial recordings, which is pretty much my YouTube channel. So I will send you all the link to the three things in the Zoom chat as well for those who are here today. Yeah. So everyone take some time to thank Jasper for his notes. Jasper the goat. Yes, exactly, exactly. Okay. So the way I'm gonna conduct this tutorial is gonna be a bit different compared to COE 691 and COE 692 because I don't really have slides on any of the topics at all. I'm gonna be using the whiteboard instead. As for the notes, I'm gonna have to see if I'll be able to upload them on time, but I'll do the best I can to assemble them after this tutorial. Because again, today I'm gonna use the whiteboard. Well, not the Zoom whiteboard though. I'm gonna use a nice little whiteboard app provided to us by Microsoft called Microsoft Whiteboard. So I'm gonna move my way over here and let's get started. So, um, let's take a look at our list of topics. I'm gonna also dig up some agenda notes on my other monitors. That's about it. Yep. So, uh, now that everyone is ready, I'm going to start with stable matching because this is actually one of the things introduced to us the at the start of the entire course. It might look a little laggy on your end. That's because my computer is running a little slow today, and also it's actually how the Microsoft Whiteboard works. So I'm going to write down stable matching. Um, and by the way, if y'all need something clarified, or if y'all like found us that I said something, I made a mistake or something, just let me know as soon as you can. Okay? You can use your voice or you can just type it in the chat. Whatever you like. Okay. So stable matching. We're going to go through what stable matching is for. So I'm going to bring up a nice little example scenario for this. I'm gonna give you all like three. I'm gonna give you all like maybe four. Um, I'm going to give you all like four people. Uh, so I'm going to write down four people's names. I'm gonna write my name in there because why not as well. And I will also uh, just write down these. Okay, there you go. So I have, for example, four candidates looking for a job, And I will also write out four companies. Okay. So, well, I'm just gonna make them company A, B, C, and D. If you want to, in the chat, just let me know. Just feel free to let me know the four companies you're imagining right now. Like, which four companies come to mind? Okay, just let me know in the chat. No need to talk about it. Okay, but let's just say that it fits with any company. Okay, so the thing about stable matching is that is we need to first look at what makes a pair stable. Okay. So I'm going to take a look at the definitions. So basically, for a stable match, which I'm going to which actually you know what, I'm just gonna do the snapshots on my tablet because like everything is gets pretty laggy when I record. So don't worry, my tablet is a Surface Pro 8, so it does have the same things as what I have on the desktop. So basically, I am given like four candidates and four companies. Yes. And I would like to match one candidate to one company. Yes, it's really really weird. Like in a really weird imaginary world where companies where like four companies trying to hire one candidate, and I'm going to put the definitions here. Whoops, 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 whoops. Okay, just gonna do this. So, I'm given like for example a set of preferences. I will also draw out the preferences, but like that will come a little later. But I will be given a set of preferences among the candidates to companies, and also a set of preferences of companies to candidates. So, for example, I'm gonna like keep right. I'm gonna scroll down here, and let's just say that I'm gonna draw a nice little table here. Okay, and these are the names. I'm going to write them down. Adam. I'm just gonna use I'm gonna use a shorter pen, a narrower pen. Oops. So we have Adam, and then we have Ben, and then there's me, and there's Dina. Okay, and I'm going to list out the first, second, third, and fourth choices. So for the first choice, Adam prefers B, and then Ben prefers C. I prefer A, and Dina prefers C as well. And then I'll do the same for second, third, and fourth. Fourth preferences. And I'm going to just assign them randomly. B, B, D, and then this will be A, C, C. Okay, C, A, D, B, A, C, D, B, and C, B, uh, A, D. Okay, something like that. So I'm given like my preferences of candidates to companies, but we also need to be given the other way around. So I'm going to zoom out, move this over, and I will now list out the companies. Uh, First, second, third, and fourth. So I'm going to write out the companies. So A, B, C, and D. And for the first, second, third, and fourth, A prefers Adam. Uh, B prefers Dina. C prefers who should this prefer? Ben, and D prefers Caleb. Okay. And I will also like just uh randomize the preferences as well. Oh, we got some people here. Um, by the way, for the people who are just joined in, this tutorial is being recorded, and I will have to take a look at whether I can make the notes on time. So for now, I won't be able to provide any notes at the end of the tutorial because I have to assemble them myself. So we have so we're looking at the stable matching problem right now. So you all are not far from late at all. So I'm going to randomize this stuff. Dina and okay, so company A has these preferences. Company B um has these preferences. Okay. Um, company C has these preferences, and company D has these preferences. Okay. So, um, so I'm given like the sets of preferences from the two sides, and now I want to take a look to see to see if we can create four stable pairs. So that means assuming that one of the companies has an assigned pair, the company somehow would a company with a currency unstable pair would prefer some other candidate rather than the one they are paired with right now. Okay, so I'm going to so basically for example, for now I have for example, let me take a look. So for example, if Adam is paired with B, but the thing is, B, but then Ben came along. Ben came along, but B likes Ben better compared to Adam. So, so that means this pair right here, oh, this pair right here is unstable. Well, this is one of the unstable pairs because, again, the company would rather take Ben as opposed to Adam. So, I'm going to get rid of the highlights, if I can, that is. And I'll take care of Adam's highlights as well. There you go. So this is unstable. So we need to give out the list of stable matches so that each company would be happy with the candidates and each candidate would be happy with the company. A lot of times, you will witness that like the company may have offers given to some people they prefer, but the problem is that sometimes the candidates prefer some other top company and then they just denied the offer. So that's what's happening there. Like basically we're just playing a game of reneging offers. No company likes that, but some candidates just don't care. Okay, so let's take a look at an algorithm that helps us take care of that helps us take care of giving out the list of stable matches. So this is called the propose and reject algorithm, which is also known as the Gale-Shapley algorithm. Uh, and what's how we do it is that oh boy, um, this is too big. Okay, so how we do it is I'm gonna scroll down here. So how we do it is that we initialize each candidates to be free. So for now I'm going to circle the entire thing. I'm gonna copy everything down there, and I'm going to align them properly. So what we're doing here is that first I want to initialize each candidates to be free. For now, we're just assuming that since nobody has a highlighted pair, we're gonna assume that they're free. Okay, and how we're gonna do that? Uh, what we're gonna do next is that while some candidates is free, we're going to assign the candidates their first preferred company. So in our example, we have Adam, who is free right now, and we're going to have Adam apply to B, and B is going to take Adam for being the third preferred. Okay, neat. The next one coming along is Ben. Uh, Ben is free, so Ben will apply to his first preferred company, which is C. Now C, because C prefers Ben the most, and while C is currently free, we can have C be assigned to Ben. That's good. Yeah, congratulations, Ben. You got your dream company. Um, now it's my turn. So how about me? I am free right now, and I would like to apply to company A. Okay, I applied to company A. A, seeing that I applied first, will for now string me along. So they're gonna take me in. And finally, D for Dina. Dina wants to apply to C as well, but the problem is that because C is taken by their very first choice, their very first preference, Dina is outright rejected. So basically, she's rejected, and that would mean Dina would have to then apply to company B. Okay, now look at company B. Company B right now is occupying with Adam here, but they like Dina the most. So so basically, what do they do? This is extremely wicked, and I am very sorry, Adam, but the company is just gonna rescind your offer. Normally in the real world, you don't see that happen a lot, if not impossible. So they're gonna take Dina instead. So they literally just rescinded Adam's offer, and they will just give Dina the offer instead, and Dina will just accept that. But then that means that Adam will need to take a look at other companies. So that means Adam is free again. And Adam will just say some really bad things about the first company he applied to, and he will move on to D. Okay? So now we still have Adam who is free. So let's take care of Adam for now. Adam applies to D, and D, while preferring me, is going to take Adam. And well, that's it. It's going to take Adam. And well, do we have any free candidates? No, we don't. We don't have any free candidates anymore. So that means we found ourselves a stable match, a really stable match. So Adam will go to D, Ben will go to C, for me, I will go to A, which I'm really happy about, and Dina will go to B instead. Beautiful. So this is a really simple case. Feel free to play around with like all like other cases. But let's just say that there are just to say that there are many different types of matchups you can do. This is just one of them. Okay. Okay. So it's been 30 minutes and I've only been talking about the first topic, which is stable matching. So yeah, yeah. This algorithm is pretty fun to follow too. Yeah. Okay. I'm gonna move on to the next topic. So for the people who are coming here, um, who have just come here, I mean, if you have any questions or if you would need me to clarify something, just let me know through your voice or in the chat. Okay. All right. I'm gonna move on to the next topic in the in the list of topics. I'm going to be addressing let's see, graphs. So we're gonna take a look at like some graph related stuff, just so that we can uh, just so that we can like do a nice little recap on it. So basically, a graph is just it consists of nodes. For example, you can mark this as one, and then you can also just draw some other nodes, one, two, three, and four. And then each node will be connected to zero or more edges. So I said zero because some of them would like to stay isolated for some reason. Who knows? So some node will be connected by edges. There are different kinds of graphs you can do here. You can also draw many different types of edges like this. Okay, so this right here is a, hang on, let me use blue here. This is a node, or you can actually call it a vertex. In plural, that would be vertices. And this is an edge. Okay, so I'm sure everyone knows this. This is COE 428 knowledge, and you should not forget about this because this is one of the more commonly used data structures throughout interviews. Okay, so how do we search through a graph like this? There are two ways. We have so for searching, we have BFS, which is breadth first search, and DFS, which is depth first search. So for BFS, you're going through the nodes like one layer at a time. So for example, let me write down BFS, and I'm gonna scroll down here. So BFS. So I'm gonna start by splitting my random graph into layers, and I'm going to make a new one. Okay. This will be connected here, and then 4, and then this goes to 5, and 4 will then go to 6. Okay. So I have a graph looking like this, okay? So the first thing in BFS is that I'm gonna start by picking a node, okay? Right now we're using an undirected graph, so that means like you can go back and forth through the same edge. So I'll start with number one. Okay, we process number one, and I will draw out a nice little set here. I will add number one into my list of visited nodes. Okay, so this is my visited nodes. I'm going to now go through I'm going to now move to my next layer. I'm going to at least show you the layers. This is layer 1, 2, 3, and 4. Okay, so 1, 2. Actually, I shouldn't have done that. I'm gonna use a green pen for this. 1, 2, 3, and 4. Okay, the green numbers are the layer numbers, and the green boxes highlights the like cover the nodes in that layer. Okay, I'm gonna start with number 1, and I'm going to add. I'm going to then explore the layers that one is connected to. And one way you can do this, and I'm going to scroll down here, is you can actually use something like a queue to keep track of like where which node you want to process next. So for the queue, I've already taken care of one, but I will also then take care of 2 and 3. Okay. I'm not gonna close that curly bracket because like we still have some things to add there. And then um, I'm going to pick out my next thing in the queue, which is 2. So we've already processed 1. We've added 2 and 3 to the queue. So now we process number 2 in the queue. So number 2 is going to be added to my visited set. And it will also then explore 3 and 5. So I'm gonna add 3 and 5 to the end of the queue. Notice how I added a duplicate into the set. Whenever you find out that this node's already visited, you just don't do anything. So we've already processed 2. So now we can look at 3 because that's next in the queue, right? So 3 is right here. Um, and 3 is connected to 4. Now, when you're implementing the algorithm, most likely you'll also somehow go back to the previous edge. Um, that's okay as well, as long as like you stop the node from being double counted, you'll be fine. I'm just gonna assume that the algorithm's good enough to not do that. But feel free to go along, but with like a duplicate nodes for like somehow going back for some reason. So I'm going to add a 4 into my queue because that is my new node. And I'm gonna go through my next node in the queue, and that's also 3 because before 3 was unexplored somehow. Because 3 was unexplored until like just now, but like it's added twice. So there are cases where like the same node will get added twice regardless. So make sure you check to see whether you have visited first. Because we've already visited this, we could just cross this out. Next is the number 5. Okay, so we're gonna look at number 5. Number 5 doesn't have any nodes, so oh, actually I forgot to add number 3 here. So number 3 is already here. And I'm going to now look at number 5. So before visiting number 5, um, before visiting number 5, 3 is added already to the queue before the double counting happens. Yeah, sorry. If I somehow like confused all of you, yeah. That was my mistake over there. That was my mistake. So the first number 3 in the queue just puts it into the visited set, and then the double counting happened in the next number 3, so that does nothing. And now we're gonna go through vertex 5, So number 5, and I'm going to cross this out, and I'm going to add it to my visited. And number 5 doesn't have any connections, so we're done for. Like, or rather, by connections, I mean like unvisited connections. So now we're gonna take a look at number 4. So which is over here. Number 4, I'm gonna cross this out, and I'm gonna write number 4 here. And this number 4, because number 4 has a connection to 6, we're gonna add number 6 into our queue. And I can tell you that like this queue is like the very very last thing. This thing is the very last thing in the queue, because number 6 is actually the very last unvisited node. So we're gonna add that into my visited set, and that's it. And because 6 has no connections that are unvisited, we're done. So I can cross number 6 out. Okay, so that's BFS. Can you explain the double count part again? Okay, so the reason why we have a double count is because there is a cycle on the left side right here. That's part of the reason. And we have so before. So let me like at least show you the order. So we paste number 1 to be the start point. So number 1 gets processed first. And then we go through, we put number 2 and 3 into the queue. Okay. So so we picked out number 2 because that is right what's next in the queue. And we're going to mark it as visited by marking the pink number 2 as like as the position in the visited order, or the visiting order. So number 2 is visited like in the uh like number 2 is the second to be visited. And because at that time number 3 was not visited, it will actually add the number 3 the second time. The first time is when number 1 adds number 3, and the second time is when number 2 adds number 3. But that is because in both times number 3 is unvisited. Okay? So then number 3 comes along, gets taken as the third to be visited, and then the number 3 is taken out again the second time, because remember we added the number 3 twice. And then the rest happens. So 3 to 4, 3 adds 4, 2 adds 5, and then 4 adds 6. Okay? Yeah, good question, and I'm glad I'm able to explain this thing properly. Okay. Okay, so let's do DFS as well before we go, because like there isn't like um DFS, you've all already done this before. You can do this recursively or through the use of a stack. Oh, we have a couple of people coming in here. Okay, so we have one. I'm going to draw the same graph, and for 6 and 5. Okay, so I'm going to draw the same graph here from the BFS, and this time we're gonna dig through it with DFS, which is depth first search. Can you scroll the screen a bit up? So so for you, Ishan, like this is just graphs, and then so this is just me like labeling node and edge, and there are two ways to search, BFS and DFS. We have just finished BFS, so I'm going to scroll this up a bit. Yep, that's about it. So if you have somehow missed it, feel free to look back at my recording, or feel free to look at the lecture notes because they explain much better than I do. So, so let us let us do a bit of DFS. So, just like before, I think I should get used to using the pen to do the picking for me, for the pens. Um, so I'm gonna write down the same visited list. Okay. Okay. So this time, I'm going to start again at 1, and I'm going to I'm going to pick one edge. In our case, I'm going to pick 2. So pick 2. So 1 is going to be visited, and then I will pick 2 by traveling through the to the bottom yellow edge that I highlighted, and 2 gets visited. We're gonna go as deep as we can until we hit either a visited node or we hit we hit a dead end. So we're gonna go through maybe, well, in ascending order, we're gonna do 3 next. Okay, 3. But 3 travels to 1 and that's already visited. So we do nothing there. So the next thing is is well, where do we go next? So we either go through, we can, so the choices right now are going to 5 or going to 4 from 3. If you were to be implementing this using a stack, you will actually pick 4, because like 4 would be the late, because assuming that 4 gets added before visiting 1, like uh because assuming that 1 and 4 are added like the latest right now, you would actually pick 4 first, which comes after 1, or the opposite. But just know that like these two will go first, because how a stack works is that the latest things will come out the first. It's called last in first out. So assuming that we're using a stack, actually I'm just going to actually I'm going to try like I'm going to just try this. So one goes first and adds 2 and 3. 2 is processed and adds 3 and 5. And then and the 3 gets processed. Oh, actually, wait. 2 and 3 in the opposite order. So next, we're going to handle 2, which adds 3 and 5. Oh, we got some new people here. And then we keep on picking the top. So 3 adds 4 and 1. And 1. I don't have space here, so let's move this down. 4 and 1. Now, 1's already done, so we're going to pick 4 next. So now we're going to visit 4. So that's if you were to be implementing this with the stack. So 4 will also add 6 we're going as steep of a chain as possible. So now we're gonna go and get 6. So 6 gets visited, and it and 6 will add nothing. Okay. So now that 6 doesn't have any other nodes to add, we're gonna keep going down the stack, and we're gonna pick 5 next. So 5 comes last. And finally, we process the other nodes. We empty out the stack. 3 comes after, but 3 is already visited, so we don't do anything. So what we ended up having is that 1 gets visited first, and then 2, and then 3, 4, 6, and 5. We go as deep as we can, and then we go back. And then we go back to take care of the other branches, or the other paths. Okay. Okay, so that's DFS. So we've taken care of like the really basic things about graphs. There are also other topics. For example, like bipartites, and some applications, and like there are also different types of graphs, like a directed graph goes only one way. Okay, so a directed graph has edges represented by arrows like this, and I'll scroll down. Don't worry, I'll scroll down. Here you go. Here you go. Here you go. So we have a directed graph, um, and we also have a weighted graph as well. So we can split we can categorize graphs using two categories. We have hang on, let me just get rid of the mail here. So we have so for a graph, we can look at directed or undirected. And in there, you can also make it weighted or unweighted. Same thing for the undirected graph as well. So for a weighted graph, you already know what that is. It's basically edges having some kind of value, like a cost. Okay. Like for example, I will assign them like random numbers like this. Okay. I'm sure like this is already covered in COE 428, so I'm not gonna go inside it too far. Okay. So yeah, there you go. That is BFS. Oh wait, no, that's graphs. Okay. Moving on. I'm gonna move on to greedy algorithms. So greedy algorithms. This is actually an interesting family of algorithms, and it is used for optimizing stuff. Well, it's one way to optimize stuff actually. And I'm going to move my canvas like this. Okay. So I'm gonna give you so basically in the lectures we have taken a look at greedy algorithms in graphs. Give me a moment. I'm just going to okay. So I'm going to look at greedy algorithms now. And for greedy algorithms, how it works is that how to identify if an algorithm is greedy or not. So an algorithm is greedy if it requires if it involves building up a solution in smaller steps. So basically, you started you choose some kind you define your starting point somewhere, and you're going to keep optimizing your solution by looking at what's locally optimized, by like going for a locally optimized path. So locally optimized means it's not over. It doesn't have to be overall optimized, but like in that small piece, for example, you're gonna look at we're gonna look at shortest paths, for example. Maybe at one node, the paths going to it will take like we're gonna use like some we'll use sorry we'll use Dijkstra's algorithm to locally optimize like each visited node to figure out the shortest path you're gonna take that you can take to get to your endpoint, for example. So it involves like cutting your problem into sub problems that where the overall answer will come from the optimized answers of to the sub problems. Yeah, yeah. Without me drawing this, it gets really confusing. Uh, but it does involve, but it is really useful in certain optimization cases. Okay, so does that answer your question, Ishan? You can follow up in the chat
Yeah,
as well.
yeah, thank you.
Yeah. Okay, you're welcome. So, I've already explained the definition of a greedy algorithm. So we start small. Well, we start off with a piece of the problem, and we're gonna find the most optimal thing, optimal answer in the piece, and we will slowly build up the pieces to give us the most optimal answer to the overall problem. Let's try shortest paths. Now, just to let you know, greedy algorithms is a really huge family. So aside from graphs, it can also apply to problems involving arrays and even strings. So feel free to look at lead code for that stuff. Okay. There's one that I really like, which is our longest palindrome. Uh, that requires you a little knowledge of greedy algorithms because that involves like maximizing each like some piece in the string, for example the letters, or for example the letters that make up the original string. Okay, moving on back to graphs. I'm going to give you a network. Okay, I'm going to give you a really short network because I don't have a lot of time. I'm going to have a node called S, and then I'm going to draw some nodes. um, and 4, and um, I'm going to do this. I'm going to get T as the end. Okay. So S is your start, T is your ending point. Okay. And I'm going to assign each edge a weight. Okay. So people, you can take a look at the graph here, or this little network, and I'm going to and to start with Dijkstra's algorithm. How it works is that hang on, let me scroll down to the algorithm itself, and I will also like paste it as well. Let me see greedy algorithms. Let's see. So how the definition explains it is as follows. So it looks like this. So we need a set of maintained nodes. Uh, Basically they are your visited nodes. I'm gonna copy this and I'm gonna paste it. Um, go. So we're gonna maintain s as our visited node. At first, it should be empty. Um, and the way we're going to look at the next node to pick after s is we're gonna use a priority queue. Okay. Now, the way I'm gonna write this priority queue is that it's not in the order of like a smallest cost, but we do have but we will pick them out in that order. Okay. So let me just go ahead and think about this one. So I'm gonna list out all the nodes for now. 1, 2, 3, 4, and T. S1, 2, 3, 4, and T. Okay. Now this is not in the order of not in the right order. So in real life, should should be ordered um should be ordered by uh by ascending weight. Ascending local weight. Now local weight is basically the weight cache type of thing we're gonna kind of mark in each node. For example, so basically they're the little numbers you see in the lecture in green, and I'm gonna do the same here. I'm gonna start S with 0, and the others are gonna be marked as infinities, positive infinities, of course, not in negative. Okay, I'm gonna start with S being having, and the algorithm requires me to, oh, we got some people coming in. Okay, so S is because S has the cost of 0, which is the smallest among the current priority queue. We're gonna take out S. Okay, so S is brought up here, and we're going to update the nodes it is connected to. So we're gonna travel through all the edges, and we're going to mark, and then we're gonna do a comparison to see if the total path to those nodes thus far are gonna have a slow are gonna have a smaller total weight. I do not know how to speak today for some reason. So I'll give you for example, we're from S to 1, which is connected by an edge with weight 3. The new total would be calculated as 0 from S plus 3 from the edge itself, and that would be equal to 3. And the good thing is it is less than infinity, so the new so we're gonna assign this as the new local cost. I'm gonna do the same to number 2. 0 plus 4 from the bottom edge is 4, which is also less than infinity. So this new node, this new cost is gonna be 4. Okay? So that's it. Now, we already have dealt with S, so the next node we're gonna take care of is, well, the one which has currently the smallest total, which is 1, with 3 being the smallest total. So let's take out 1. Visit 1, and we're going to look at each connection 1 has. So 1 is connected to 3 and 2. Let's look at 2 first. So 2 has so from 1 to 2 we need 2 more. So that means from number 1, which now has a local cost of 3, we're gonna compute the new total for 2. 3 plus 2 is 5, but that is bigger than 4. So what do we do? Absolutely nothing. So how about so this is already visited. So how about number 3? So how about going to 3? 3, so for number 3, we have we first have number 1 locally having the total of 3, and then we add by 8. So this is 11, which is less than infinity. So therefore, we give it 11. We give the new total 11 to number 3. Okay? So, what's the next node from the priority queue? Well, from the priority queue, you should have number 2. Okay? So number 2 has the smallest is the unvisited node with the smallest local weight, so which is 4. So we're gonna visit 2, and we're gonna take a look at its connections. Okay? So from 2 to 3, we have 4 plus 9, which is 13, but that is bigger than 11. Okay? So because it is bigger than 11, we're not going to do anything. Now we look at from 2 to 4. So from 2 to 4, we have 4 plus 7, which is 11, which is smaller than infinity. So because of this, let's give it 11. Let's give number 4 11. Okay. So now we have 2 nodes having the local weight be 11. So we're gonna pick out 3. Okay? So number 3 is gonna be visited, and we're gonna visit the only connection it has, which is T. Okay? So from 3 to T, we have 11 plus 5, which is 16. And that's less than infinity, of course. So we're gonna give T for now the weight of 16, the total weight of 16. Okay. There is now what's next in the priority queue? Now that we have dealt with all the edges from 3, we have 4. So let's take out 4. From number 4, 11 to T has a total cost of 11 plus 11, which is 22, but that's bigger than 16. So what do we do? Absolutely nothing. And that's the only connection it has, so okay. So for the very very so the very so for the very very last thing in the in in the priority queue, we have T. So let's take away T. So now T is the last to be added to the visited, and it has no other connections, so we're pretty much done. So what should be the path to get to T while minimizing the cost? So that would be 0 from S to 1 to 3 and then to T, because that's the path that will lead us to the optimized total. Okay. So in the exam, it is likely that you'll encounter a some kind of greedy problem, and you may have to run the algorithm in your head. Maybe. Okay. Do you get the answer from hit and trial? um, like if you like, do you mean like, do I get the pass from hit and trial? It's hard to say what I actually I haven't even thought of that yet, but hit and trial, like S23T isn't the shortest, so I hit S4T. Okay. Um, like how come are you able to get from S to 4 directly? So hit S and then finally get S13T. Oh, okay, maybe not the first, but say after the first. Hmm. So after S and then 1, okay, 2 is shorter. Now, do note that when I processed S, I looked at all the connections. So at that time, from S to 1, 1 will have the local weight of 3, and 2 will have the local weight of 4. I looked at all the connections, and the priority queue, remember, is orders the nodes by their local weights, so ascending local weights. So at that time, like node 1 will go first because it has 3, and 2 will come after. Yeah, yeah, yeah. So for this algorithm, like you do have to look through all the connections, all of them. Don't just pick one. Pick all of them. Like look at all of them and then relax them. That's all. Okay. So it's 7:15. There's one more algorithm for greedy algorithms called minimum spanning trees. So let's go ahead and look at that. So for minimum spanning trees, it's actually at least a little bit simpler to explain, but it is also a type of greedy algorithm because it builds edge by edge. So we're looking at each edge and we keep on taking the smallest. So we're being a little bit greedy. The only time we don't take an edge is if like that edge would make a cycle. That's about it. So the minimum spanning tree will always give us the tree with edges adding up to the smallest total from the given network. Okay? I'm going to give you the same network, And I will also make some modifications. So from here, I'm going to do this. Okay. So um, we're given some kind of network, and I'm going to keep picking. I'm going to try using Prim's algorithm to pick my edges. Okay. So let me take a look at where the Prim's algorithm is on my end. So so how it works is that we start at some vertex. Let me come on, come on. There you go. Ah, whoops. Come on. There you go. Smaller. There you go. So here's how it works. So we start with vertex 0. So we're gonna use Prim's algorithm. Crisscross algorithm it's a little different because it looks at all the edges, but Prim's explores the edges from a given start point. Okay. Now, as part of the changes, I'm going to make my notes a little bit um, like this, like 1, 2, 3, 4, 5, and 6. There's no S or T, but you can label them like that if you want. I'm just gonna make it look like this. So I'm going to pick number 1 as my starting point. Okay, I will highlight this in green. Okay, so so I'm going to create a priority queue of edges to be recorded. From number 1, we're gonna add 1, 2, and 1, 3. Now, again, this is not properly ordered because I am very lazy. But this is actually one way you can do minimum spanning trees. Why can't we use the previous version? Um, oh, for me? Oh, why not? Well, it's just me having a preference of like using all numbered nodes in this type of problem, but the thing you store in the nodes can be anything. It could be a number, it could be a string, it could be anything. So it's actually up to you. And I also added one extra edge here. But it doesn't really matter. It's just me trying to design a random network. But yeah, that's about it. You can label your nodes with anything. Okay, so I'm gonna add 1, 2, and 1, 3 to my priority queue. Now 1, 2 and first I'm gonna pick 1, 2 because 1, 2 is gonna be the first in the priority queue, being the smallest explored edge. Okay, and then uh and then I will explore 2. Okay, so let me take a look. Let me also do one more thing. I'm going to also write out the visited nodes, and right now 2 is visited. So 1 was visited at first, then we add 2 to the list. Next, I will add some more edges that come from 2. So in our case, we look at 2 to 3 and 2 to 4. Okay. So by the way, the green thing is actually the will highlights the edges that make up the network. So the next thing I'm going to look at is how about from so among the three unvisited edges, 2 to 3 having the weight 2 will be first in the priority queue now. So we're gonna add that to the list. And because there are no cycles, we can add it, and that's fine. And we're gonna add number 3, which was unvisited, into our visited. Because we're gonna process this stuff by adding from 3 to 4 and then 3 to 5 to our list of edges, our priority queue of edges. Okay? Now, among all the edges that we haven't visited yet, there are 4 right now. 1, 3 is gonna be the smallest here, but because there is a cycle, we're not gonna add that. So we're not gonna add this. So let's pick the next one. The next one is from 3 to 5 because 3 to 5 has the weight of 7, which is the lowest so far, and there are and because there are no cycles, we can use this. We can use this. Oh, oh dear. Um, okay, hang on a moment. There you go. Here you go. And then I'm going to draw it again. Okay. The next thing, now what's next? We need to visit 5. 5 is visited. So now 5 is marked as visited. 5 was unvisited though. And from node 5, we have one edge that comes from it, and that is 5 to 6 with the weight of 11. Okay. Oh, let me write this thing a little properly. Okay. What's next? So among the three edges that to be visited, we have 2 to 4 to think about as well. So let's pick out 2 to 4. And because 2 to 4 won't make a cycle, we're going to add this. And we're going to also mark 4 as visited. Now, the number 4 is going to add some new edges for us, and that is from 4 to 5 and 4 to 6. Okay, so we have 4 unvisited edges, and right now the smallest one is gonna be from 4 to 5. But again, because 4 to 5 would make a cycle, we're not gonna add this. Okay, just like how 1 to 3 would not be added as well. Okay, what's next? From 4 to 6. So let's take a look at 4 to 6. The undo button is not working, by the way. So from 4 to 6, we will take this because there are no cycles being made here. And, well, number 6 is going to be visited. Okay. And finally, we will, and that way, so with that, number 6 is not going to add any more edges, and that's actually going to be the end of the priority queue. So there are 2 more we're gonna need to pick out. We have 3 to 4 and 5 to 6. So the next in the priority queue is 3 to 4, which has the weight of 9, but that makes a cycle, so this would be rejected. And same goes for Same goes for 11, which will uh, same goes for 11, which will be rejected as well because that will make a cycle between 4, 5, and 6. And there you go. So what is the total cost of this thing? So we have 3 plus 8 plus 5 plus 2 plus um, so 3 plus 8 plus 5 plus 2 plus 7, which is 25. And that's it. So that's the total. Okay, so it's about 7:30, and we have like 4 more topics to look at. So let's go to backtracking. Okay, so backtracking. Uh, Let me just scroll down here. So we have shortest paths and minimum spanning tree. So now let's look at backtracking. I'm going to turn this. I'm going to turn off my notifications because that is going to kill me at this point. Because that's going to kill my attention, more like. Um, okay, so let's take a look at backtracking, shall we? So backtracking is actually a brute force algorithm where you try to search for a solution, but if you somehow like find one that's if you somehow like reach a dead end, you're going to go back. You're gonna reverse it. You're gonna retrace the steps, and you're gonna try a different way. So I'm only going to do one of them, and that is going to be rats in a maze. But there are also n queens that you can take a look at. Um, so I'm going to do rat in a maze. So for rats in a maze, I'll give you some uh I'll give you all some cells to look at. I will make a 5 by 5 grid with a little dead end here. I'm gonna erase this one, and I'm gonna mark the starting point in red. So this is the start, and I'm going to mark the ending point with green. Notice how I'm marking zeros in them as well. So this is the end. Okay, and I'll also mark all the other cells as zeros. This means they are not part of the solution, but they're empty. Now x's means a wall. Zeros means empty empty cell, and 1 means path. Okay, so what I want to do is I want to find a path from start to end. And how do we do that? Well, I'm going to give you I'm going to give you I'm gonna take let's revise what we have here. Okay. Oh, by the way, you can only go down or right in this type of algorithm, but if you need to do like all 4 directions, you might need to do some extra work there. Okay? So let me make this a little bigger. Um, okay, I'm just zooming in, everybody. Don't worry. No need to worry. Okay. So, how are we gonna do this? So first, I'm gonna demo this. We have we start by creating this matrix here on the left, and I'm going to put my rat at the starting point. So basically, So basically, you're trying to solve this. You're trying to solve. So I'm gonna let M be my maze, and I'm going to start at row 0 and index 1. Okay. So basically, we have. I'm gonna define solve as like the matrix M. So maze is your matrix, and then row and column. And then I'm going to I'm gonna start at the start point. So that means M01. So this whole thing is M. Give me a moment. Okay. Oh, whoops. Um. Okay. Yeah, it's very weird, but like again, my undo button's not working. Okay. Let me try this again. So M here is x x x x x. This is goal. Okay, and then all the rest are zeros. Red is 0, and this here is a 0 as well. This is the end, and this is the start. Okay, so what I'm gonna do is I'm gonna start with I'm gonna start at m equals to uh row 0 and column 1, so that's here. So that's basically here. And I'm gonna look at like what's to its right and then down. Okay? So to its right it's a wall. So basically we're gonna look at m 0, or actually, oh, it goes down first and then right, according to the algorithm. So let's go down first, which is here. Okay, so going down, we have m at 1 1. So m at 1 1. Oh, I will mark this as part of the solution first, and I will also mark this as part of the solution because this is an empty cell. Next, I will look at what's below it. So, and I will mark it a 1. So that is solve m to 1. Okay. Okay, now we look at what's below it. That is 0. So we mark it a 1. And then we look at solve m3 1. Give me a moment. 3 1. There you go. Okay. Now, what happens if I go down now? We have a dead end. Well, below is a wall. So at so solve 0 1, we're gonna move down, move down, move down, move down. Now at 4 1, because there is a wall, we're gonna backtrack it. We're gonna backtrack. and uh, we're gonna backtrack this, and we're gonna try the right instead. So we're gonna backtrack and try the right. Okay. So we're gonna backtrack, try the right. Okay, the right side looks good. So we're gonna mark this as a 1. Okay. And then we're gonna look down again, but this doesn't work. So from here I'm gonna do this m uh so basically we go through uh we go through M32. We go through M32 instead. So down, 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 down. Okay. Down, down, down. Okay. So that's basically taking the right. Okay, the arrows are actually confusing me as well, so I'm just gonna write like this for now. But I'm gonna keep the cross because that means we're not doing it here. Now next, which I'm gonna write on the other side, we're gonna look at whether we can solve if the rat is placed at 4, 2. 4, 2 is a wall. Okay, so 4, 0, 1, 2, 3, 4 is row 4 is down here, and column 2 is down here. So that's a wall. That's bad. Oh, come on, come on, whiteboard. Okay, and also let me reopen whiteboard again. Just so that I can like regain my undo thing again. Okay. Okay, so number 7, we've already figured out that like this is a wall. So we're gonna backtrack and we're gonna try the other way, which is the right. M5 oh, actually wait. Um yeah. M33. Okay, so M33, so 0, 1, 2, 3, 0, 1, 2, 3, so it's right here. This is all right. So let's go ahead and change this to a 1. And then we're gonna also look down at M43. And guess what? M43 is the goal. So we can mark it as a 1 and we're done. So yeah, backtracking means that if you land on a wall, you go back to your previous cell and look the other way. If both ways don't count, then you would have to go back, retrace the steps, look for the other way in the other steps. So you keep going back until you find another path, or you find out that there is no solution at all. Okay, and that's it. Okay, it is 7:40, so I'm going to so that is an example of backtracking. There's another one which is dynamic programming, which would actually take quite a while. So let me give you one which is coin change. So dynamic programming, I'm just gonna do coin change. Okay. Yep, and I'm just gonna get the people here. So I'm gonna do coin change. So you know that like in Canada we have We have 50 cents. We have 5 cents. That's is that I forgot what it is. Okay. Okay, I know that a dime is 10 cents. In that case, there's a nickel, a dime, a quarter, and then a loonie and a toonie. Okay? So this is here. And for example, if I want to make change, I want to make some change. For example, 40 cents. So how do we reduce the how do we make that change without having to give customers excessive coins, because nobody likes to keep too many coins around. Well, one way you can do this is you go through like well, if you do it the greedy way, you would like you would sort the coin types by their values, and then you just go through them and take the maximum they want while subtracting from the total you're trying to make. But that doesn't really always work, because maybe there is some other way. Uh, like for example, like for example, like if you do it the greedy way, you would like list it out 0.25, 0.1, and 0.05 like this, and then you would just take 1, 1, and 1 of the quarter, dime, and nickel, or 5 cents. But what if we introduce a new coin, which is 20 cents, and then we do this. While the greedy method is well, if you take this greedily, you will end up like just taking one of this, and one of this, but that makes 3 coins. Instead, you could have taken 2 of the 20 cents instead. So I'm going to write this. Like you could have you could have taken just 2 of them, which I will mark in red. Actually, never mind. I'm going to mark the wrong one in red, and I will also take this as green. Okay? Like you could have taken like 20 cents twice instead of taking 3 coins. So, how we do dynamic programming is that we split oh how do we do dynamic programming is that we split our problem into again like smaller pieces, but the way we split them, but the small piece is going to be a little bit different compared to oh what hang on. So I'm going to look at like how the okay. So basically we're going to break the problem into overlapping subproblems. I'm going to just give you the definition here. Okay, there you go. Uh, so overlapping subproblems. So we break it up into pretty much so pretty much we are solving for the same thing, but like at a smaller number, and then we're gonna keep building up the solution until we reach the target. So that is how I would like interpret this. For example, in our case, like here's how like we can make the correct change. Um, so how we can make the correct change is that we take a look at uh, how we make the correct change is that we take a look at each amount. I'm gonna scroll down here and see if we can first at least reduce the target total with one of the coins. If we cannot, then like we just cannot. We can do something like return -1 for this school occasion. Um, otherwise we can otherwise we take the coin and then we look at how many coins we would need to make the remaining change. Okay. Um, how about this? Let's try. Let me take a look. I will write down the total. I want it to be 40 cents, and I want to. Let me think about this one. Um, 40 cents, and I want to. I'm going to use recursion as I did up here to. I'm going to use recursion and I'm going to start by calling min num coins for some kind of money. For our money, I'm going to write 40 cents. Now, ideally, if you store floats like this, it should work with no issues. But like the way we store like real numbers, there are some errors in it. So we normally try to avoid this when possible, unless we're trying to display results in a certain number of decimal places. Okay, so we start by working with minimum number of coins. We start by calling min num coins of 40 cents. And this will actually, so I'm going to write down my coins. And we have 1, 2, uh, 5 cents, a quarter, and a dime. Okay, like this. So I'm going to basically, um, when we call the minimum number of coins, that would that would be equal to. We're gonna take the minimum of min num coins of 0.40. Well, we need to first look at to see if the coin would overcharge would end up overcharging the total. In our case, one would not do, two wouldn't do. We could do 5 cents, and then we can also look at doing this with 25 cents. That's fine. And then we add one for taking the so let's see, take the nickel, and then we take the quarter, and finally, for the last coin, we can just take the dime. Oh, actually, I'm just gonna add one more, cause why not? I'm just gonna add 20 cents into it. Okay. Um, I'll add one more. So minimum number of coins. I know that we have 10 more minutes left, so I'm just gonna demonstrate this, and then I will leave like the last two topics, which is divide and conquer and NP complete problems, to all of you to revise yourself. Yeah, I can't really like make it in time, sadly, but that's okay. So this one is we take 10 cents, or we take 20 cents, which is weird, but okay then. All right, so we're gonna take the minimum between these four things, and we're gonna do it recursively. So basically, this is a recursive call. So this is a recursive call, and the way we are gonna call this is minimum number of coins is that we start at 40, then we have and then this will split into four recursive calls. I'm gonna use MNC for short. 0.4 minus 0.05 is 0.35. And then we have this one. This one leads to the remaining of 15 cents. The third path is taking 10 cents. This will give the remaining as 3 cents, and we also have 2 cents as well for taking 20 cents. Okay, I'm going to draw the recursive tree here. And the next thing we're gonna do is from the 35 cents we can only do 25. We can only do the 4 coins again. So we can only do this one will lead to 10 cents for taking the quarter. Actually, I'm just gonna do this in order. 0.05 would end up having 3. Uh, and then taking the quarter gives you 10 cents. Um, Taking 10 cents gives you a quarter. And finally, taking 20 cents will give you 15 cents. Okay, I'm going to just keep calling. Uh, Basically, we're gonna recursively call this, and the tree gets more and more complex. It pretty much sucks. So one way you can do this, one way you can like make things easier. So one way you can make sure that you don't have to like call the same thing over and over again is something called memoization. This is where you have an array or some kind of map. For example, like the memo at 35, for example, is like the memo at like what is it, 15 cents. Like the smallest is what do we have? For 15 cents you can just make it with 2 coins, for example, and then you can like refer to this first. So for example, I'm just gonna write down random numbers for this one, and so on and so forth. Um, you can refer to this first. This first. Recurse recurse and add its answer otherwise. So let me just do it here. So this is actually you can use an array. You can use an array, a matrix. You can, if you want to, you can even use a hash map if you want. Just something for you to keep track of. Just something for you to keep track of, like the already existing answers. Okay. All right. So now I am running out of time for sure. So does anyone have questions you would like me to do? So memorization, you refer to the, okay, one more thing. So you look up the answer first. If there's no if like this particular parameter is not has not been looked up before, you just do the recursion and add the answer and add the answer to the map. Uh, Otherwise for the other recursions to see it. This will drastically reduce the time complexity from an exponential to something like linear to linear potentially. So yeah, that's about it. Now, my whiteboards might not cover everything, but if you have any questions, you can just let me know. Otherwise, I'm going to cut my tutorial here. I'm sorry I can't really cover everything this time. Hopefully, I'll be a little faster and cover everything you need for the exam. Okay? Yeah, see you next time, and I will stay here for questions. Oh, first, let me stop my recordings. All right, see you, YouTube.